Good afternoon, everyone. Welcome to my presentation. I'm Fariduli Martinadiatna, a PhD student of King Mongkut's Institute of Technology Latgrapang in School of Engineering. Today I'm going to present to you some of the results of my research with Mr. Joko Suroso and Professor Panarat Cherntanomwong about Fingerprint Database Enhancement using Spatial Interpolation for IoT-based indoor localization. The increasing demand of LBS or location-based services drives the development of various localization systems to stimulate new business, leveraging customer location. As we know, GPS, an established localization system, allows us to locate and track objects such as people and vehicles precisely outdoors. However, most of the time people conduct their daily activities indoor. Therefore, indoor localization system is applied to locate humans or objects in indoor environment. The fingerprint technique is the most commonly proposed technique for indoor localization because this technique provides accurate location estimation. The fingerprint technique divides into two phases, online and offline. In the offline phase, we construct the fingerprint database by collecting the signal parameter, for example, received signal strength indicator or RSSI. Then we store all the collected data to the database. In the online phase, we infer the target location by matching the actual RSSI value from the target with the fingerprint database. The accuracy of fingerprint technique depends on the quality of the database. The denser fingerprint database will increase the accuracy. However, manual data collection in the offline phase requires high effort, such as extensive labor, high cost, and high time consuming. These are the main problems in the offline phase that hinders fingerprint technique implementation. Thus, we propose to enhance the fingerprint database by using various spatial interpolation techniques to reduce the data collection work in the offline phase but still get the high density fingerprint database. The main contribution of this work are implementing classical spatial interpolations to enhance the database in our empirical data. We compare the various types of spatial interpolation techniques to find the best method for enhancing the fingerprint database. The various classical spatial interpolation techniques we use include inverse distance weighted (IDW), quadratic spline, cubic spline, and ordinary kriging interpolation. Inverse distance weighted (IDW) is a spatial interpolation method that exploits the spatial correlation of the local adjacent reference points to predict a value at an unmeasured location based on known data. For example, we can estimate a value by multiplying z1 with w1, which is obtained from inversing the distance between the green dot z1 and the red dot, z2 with w2 and z3 with w3. So the sum of those multiplication will be the numerator and divided by the summation of all weights. The second interpolation technique is spline interpolation. Spline interpolation divides the regression data line into several segments based on the reference points. For example, in the right hand figure, we have 4 points x0, x1, x2, and x3. We can model the line between those dots using spline interpolation to get the function for predicting value in the blue line. There are two types of spline interpolation: quadratic and cubic spline interpolation. Similar to IDW in this context, the ordinary kriging is utilized to augment the synthetical RSSI in the fingerprint database by considering multiplication of weight with the adjacent measured RSSI value. However, its difference from IDW, the ordinary kriging just judge the weight by using semivariogram, and the ordinary kriging starts by creating the experimental semivariogram. The second step is modeling and fitting the experimental and the theoretical semivariogram. In the third step, we calculate the weight using semivariance value, and finally we can estimate We can estimate the value by multiplying the adjacent measured value and the corresponding weights. To evaluate the effect of applying spatial interpolation on the enhancement of the fingerprint database, we use dataset from our previous work. We have conducted a measurement campaign for the localization system by employing ZigBee standard device. We applied a star topology with a sync node as target located in the area of interest, while 4 access points are placed in the corner of the area of interest. The data collection was conducted in the lobby of our building for 5 by 5 meters square. The actual setup of the area of interest is depicted in the left-hand figure, without any obstacles such as furniture and human on the floor plan, and with interference-less signal while measurement, due to the existing Wi-Fi access point being turned off. We measure the RSSI in 36 points as shown in the right-hand figure. We organized 2 main steps to examine the various spatial interpolation to synthesize RSSI to enhance the database. In the first step, we remove some RSSI values and replace them using interpolated data, as in the left-hand figure. The red cross represents the measured data retained for interpolation. Meanwhile, the blue positive sign denotes the data that is relieved and replaced by interpolation data. In these steps, we also obtain the semi-variogram model used in Kriging interpolation fits the empirical semi-variogram. The following step is to enhance the database on the measurement data. The denser database is then compared to real measurement and verifies the effect of augmentation data on the positioning error. To validate the performance of the fingerprint technique proposed, we use 4 types of coordinates of the target. The target was placed diagonally for type 1 and type 2. Type 3 and type 4 are placed horizontally and vertically by considering placement of 4 access points shown in the left-hand figure. We applied minimum Euclidean distance to compute the distance between RSSI in the database and RSSI from the target. The results show that for the ordinary Kriging interpolation, we evaluated 3 types of semi-variograms: spherical, exponential, and Gaussian to find the most fitted semi-variogram. The semi-variogram model that fits the empirical semi-variogram can be examined by finding out the smallest error of the RSSI prediction. In the figure of this slide, we can see that spherical is the fitted semi-variogram model. The overall mean positioning error generated by various spatial interpolation techniques is almost similar to the error generated by positioning using a measurement database. The cubic spline interpolation yields the same error as the full measurement database. The quadratic spline interpolation produces the most significant mean error for the most significant mean error. For the fingerprint database enhancement result, we found that for every spatial interpolation technique decreased the mean error positioning. The IDW and ordinary Kriging can increase the accuracy up to 38.2%. Meanwhile, the quadratic spline has the lowest error degradation, around 7.2%. In the conclusion, we propose a fingerprint database enhancement approach based on various spatial interpolation, and by using the spatial interpolation, the database density can increase and the accuracy of positioning increases. The denser database that uses ordinary Kriging and IDW has the lowest error positioning. Thank you for King Mongkut's Institute of Technology Latkrabang that support us to finish these works. Thank you very much.